Hello everyone. Today we'll be talking about independence. Most of you have, actually all of you have already studied independence. We know that if two random variables are independent, then their expectations can be expectation of their product is product of their expectations. We have also studied independent events. So let me start with independent events and then we will extend the definition of independence of events to independence of random variables. Okay. So how do we define independence of two events? So if I have two events, say A1 and A2, then we say that they are independent if probability of A1 intersection A2 is same as probability of A1 into probability of A2, right? This is our definition of A1 and A2 being independent. From this independence of events, we now want to go to independence of two random variables. Okay. Of course, this definition of two events can then be extended to finitely many events. And if we have infinite, so let me write finitely many. So if I have A1, A2 and AK, and if all of them are independent of each other, then probability of AI intersection AJ is probability of AI into probability of AJ for every I not equal to J. Okay, and if you take many of them, means even if you take say probability of A1 intersection A2 AK, this would still be product over probability of AI, I going from 1 to K. Okay. What happens if I want to define independence of countably infinitely many events? So if I have a collection of events A1, A2 and so on, we say that this is independent if every finite sub collection is independent. Okay. So what do I mean by this? If I take any finitely many AIs from this and if I want to write probability of their intersection in this way, and if that probability is product of the individual probabilities, then we will say that this entire infinite collection is also independent. Okay. Now this is all about independence of events and we have already studied that. In fact, you also know mutual independence and pairwise independence from your BSc days. Okay. Now we have to generalize this to independence of two classes of events. Okay, so independence of classes of sets or classes of events. Okay, so let script C and script D be two classes of sets. We say that they are independent. We say that C and D are independent if and only if probability of A intersection B is same as probability of A into probability of B for every A in script C and for every B in script D. Means if you take any two sets from these two classes and if you take their intersection, if probability of their intersection is same as product of their probabilities, then you will say that the two classes of sets are independent. By the way, I did not say that this script C and script D have to be disjoint. Okay. Why? Because sometimes an event can be independent of itself also. When would that happen? So, when can an event be independent of itself? Any idea? Let us try to see. So I want to say an event A is independent of itself. What is the definition of independence? Probability of A intersection A should become probability of A into probability of A. Right? Now probability of A intersection A means probability of A, and it should become probability of A square. So when would this happen? This would happen if and only if probability of A is either 0 or probability of A is 1. Correct? Probability of A would be equal to probability of A square if and only if probability of A is either 0 or 1. Hence, an event is independent of itself if and only if it is either an impossible event or a sure event. Okay? So, it has to be either an impossible event, that is probability of A is 0, or it has to be a sure event. Then event will be independent of itself, and it's both ways. Means every impossible event would be independent of itself, every sure event would be independent of itself. Is it okay? And are there some events which are independent of, say, every event? Let us try. So let A be an event which is independent of every other event. Can this happen? When can this happen? So let us try to see. So it is independent of every event means probability of A intersection B is same as probability of A into probability of B for every B that you can think of. Okay. First of all, because I am saying that it should happen for every B, it should happen for A also. So A can have either probability 0 or 1, only that much. Okay, A cannot have something in between, because then it won't be independent of itself. Okay, now let me try if A is equal to omega works. If A is omega, then I will have probability of omega intersection B to be equal to probability of omega into probability of B. Omega intersection B is B and probability of omega is 1. So this works. Correct? So this works, means every event is independent of omega. Okay? Every event is independent of omega. Does it work for phi also? Does it work for phi? So if I try probability of phi intersection with B, and I want to check whether it is same as probability of phi into probability of B. Probability of phi intersection B is nothing but phi, and hence it is 0, and right side, because this is 0, it would be 0. Hence every event is independent of phi. Okay, so these are two important results that we have seen. First, an event is independent of itself if and only if it's either an impossible event or a sure event, and an event is independent of every other event if and only if it is either omega or phi. Okay. Okay. Now we have talked about independence of events, independence of classes. Now we need to go to independence of sigma fields. So basically sigma fields are just classes of events. Okay, so we don't need a completely new definition. So independence of two sigma fields. So let sigma x and sigma y be two sigma fields. We know every sigma field is a class of events. Therefore, they are independent if and only if probability of A intersection B is same as probability of A into probability of B for every A from sigma x and for every B from sigma y. So if you pick one event from each of them and if you take probability of their intersection, then that is same as product of the individual probabilities. Okay. In fact, this can again be generalized to finitely many sigma fields and of course infinitely many sigma fields. For infinitely many sigma fields, what would we say? If I have countably many sigma fields, say sigma 1, sigma 2 and so on, we will say that this collection of countably many sigma fields is a collection of independent sigma fields if and only if every finite subcollection is independent. Okay. And now we come to the main definition, independence of random variables. Now that we have already defined independence of sigma fields, we are going to use that. Okay. So, two random variables x and y are independent of each other. Two random variables x and y are independent of each other if the corresponding sigma fields, that is the sigma fields induced by them, are independent of each other. Sigma fields induced by them are independent of each other. Is it okay? We have just seen the independence of two sigma fields. So if the sigma fields induced by random variables are independent, we will say that the random variables are also independent. And again, this can be extended to finitely many random variables or infinitely many random variables. Okay. Now, when can I say that a random variable is independent of itself? Okay. And can we go from this definition of independence to our usual definition of independence? So let us try that. So our usual definition of independence says that the PMFs or PDFs can become product, right? So let us try that. So suppose x and y are independent of each other. Okay, and we want to check if our usual definition of independence holds, means PMF or PDF or CDF kind of thing. So let S1 and S2 be two Borel sets. Then we want to check whether probability of x belonging to S1 and y belonging to S2, that is intersection, is it same as probability of x belonging to S1 into probability of y belonging to S2. Why do I want to check this? Because this is sort of definition that we have been always listening to. For example, when we have PMF, we say probability of x equal to x, y equal to y is same as probability of x equal to x into probability of y equal to y. So in that case, our S1, S2 become singletons. In case of CDFs, our S1, S2 become the intervals minus infinity to a certain real number. Okay, so is it true? Is this correct? So let us check. So probability of x belonging to S1, y belonging to S2 would be written as probability of omega belonging to x inverse of S1 and omega belonging to y inverse of S2. That is our definition. X belongs to S1 means x of omega is in S1. So omega is in x inverse S1. And x inverse S1 is, because x is a random variable, x inverse S1 would belong to sigma x and y inverse x2 would belong to sigma y. Okay. So let me call x inverse of S1 as say A and y inverse S2 as B, and A is in sigma x, B is in sigma y. Why? Because that is my definition of random variable. So this is probability of A intersection B. And we know because x and y are independent of each other, we know their corresponding sigma fields are independent of each other. So this is same as probability of A into probability of B. Okay. And we will again substitute what is probability of A. Probability of A is probability of omega belonging to x inverse S1. B is probability of omega belonging to y inverse S2. So this is we can say this is Px S1, Px S2, Px S1 is probability, sorry, Py S2, Px S1 is probability of x in S1 and this is probability of y in S2. Okay, so this is exactly what we have been using. Hence, the definition of independence that you have studied in BSc is equivalent to the definition of independence that we stated today in terms of sigma fields. Okay. And as I said, this can be extended to finitely many and infinitely many random variables. We will say infinitely many random variables are independent if and only if every finite collection is independent. Okay. Now, what about functions of random variables? So, let gx and hy be Borel functions of x and y respectively. And we know that x and y are independent. Then can we say that gx and hy are independent? Now what we know about Borel functions? We know that sigma field induced by a Borel function is subset of the sigma field induced by the original random variable. We have proved this, right? Sigma of gx is subset of sigma of x and sigma of hy is subset of sigma of y. Okay. Sigma field generated by the Borel function is subset. Further, we know that x and y are independent, means we know that sigma x and sigma y are independent. So suppose this is my sigma x, this is my sigma y. Sigma gx we say is going to be somewhere here, sigma hy is going to be somewhere here. So this is sigma gx, this is sigma hy. What we know is the bigger sigma fields are independent. What do I mean by that? It means that if I take any set from this bigger thing and any set from this bigger thing, then probability of their intersection is same as product of the individual probabilities. So if it works for bigger, it's going to work for smaller. What do I mean by that? Let me take any A from sigma gx and B from sigma hy. So let A be some set from sigma of gx and B be some set from sigma of hy. Because we know sigma gx is subset of sigma x, this would imply A belongs to sigma x, correct? Since this is subset of this. And similarly, B would belong to sigma y, since this is subset of this. Okay. And we know that sigma x and sigma are independent, therefore probability of A intersection B is probability of A into probability of B. Okay. So if you start with A and B from sigma gx and sigma hy, then the probability of their intersection is same as product of their individual probabilities. Hence, sigma gx and sigma hy are independent. Therefore, gx and hy are independent. So if x and y are independent, their Borel functions are also independent. So if x and y are independent, then say e raised to x and log y are independent, or x square and y square are independent, or say sin x and cos y are independent. All these things would happen. Okay. So if you have two independent random variables, their Borel functions are also independent. Okay. And of course we have our usual definition. If x and y are independent, then expectation of xy. So if x and y are independent, then expectation of xy is same as expected x into expected y. This can be proved again first for simple random variables, then for non-negative, and then for arbitrary. Okay. Because this combination of this Borel function result and expectation result would tell me that MGF of product of two independent random variables is same as product of individual MGFs. Okay, we would be using both the results, Borel function as well as expectation. Because if x and y are independent, then e raised to tx and e raised to ty would be independent by the Borel function result, and hence further expectation of e raised to tx into e raised to ty would also be written as product of the expectations. Okay. Now we are also going to study something called as Kolmogorov-01 law. Okay. What is Kolmogorov-01 law? For that we need first definition of tail sigma field. What do I mean by tail sigma field? When we dealt with sequences of real numbers, you must have studied the result that for a sequence of real numbers, limit does not depend on the first few terms. So even if you have say two sequences where first few terms are different, but if everything else is same, then the limit is going to be same, right? So tail sigma field kind of captures something like that. So let me have a sequence of random variables. So let x1, x2, xn dot 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 be a sequence of random variables. Then let us define Cn as sigma field generated by xn, xn plus 1 and so on. Okay, so everything starting with xn. Okay. So Cn plus 1 would be sigma field generated by xn plus 1 and so on. So as you can see, Cn plus 1 is subset of Cn. Okay, Cn plus 1 is subset of Cn. Therefore, Cn is a non-increasing sequence of sigma fields, basically decreasing, but we call it non-increasing to accommodate for equality. So Cn is a non-increasing sequence of sigma fields. So what would be limit? Limit would be intersection. So let me define script t as intersection over Cn's n greater than or equal to 1. Okay. Since it is decreasing, intersection is kind of its limit. Okay. Cn is a decreasing sequence of sets, so its limit exists, and that is intersection. And because every Cn is a sigma field, and because we know that intersection of sigma fields is a sigma field, this T is also a sigma field, and it is known as tail sigma field. Why? Because you are kind of taking the tail part of everything, the right side part of everything. When you take Cn, you leave out first n minus 1. You start from n onwards. So you are always taking the tail. Hence it is called as tail sigma field. And tail events are events which are measurable with respect to tail sigma field. Okay. So events measurable with respect to tail sigma field. Similarly, you have tail random variables. Those are random variables which are measurable with respect to tail sigma fields. So limit or limsup or liminf, if they exist, they would be tail random variables. Why? Because they don't depend on first few things. Let me try to explain in the context of real numbers. It's easier there. So if you have a sequence, say an, defined as n for every n less than or equal to 50, and then 1 by n for every n greater than or equal to 50. Okay. And then you have another sequence bn, which is defined as 1 by n for every n. So for first 50 numbers, an and bn are different. Okay, so an is not equal to bn if n belongs to 2, 3, 4 up to I need to delete equality from something. Okay, 2, 3, 4 up to 50. An is not equal to bn. However, after 50th number, an and bn are equal, and we know that both would converge to 0. Okay, why? Because limit of an doesn't depend on these first 50 terms. So such events or such random variables which are not dependent on first few finitely many terms would be tail random variables. Hence, limit or limsup or liminf, if they exist, they will be tail random variables. Okay. Now we are going to make use of these tail random variables in Kolmogorov-01 law. So let me state the law. Kolmogorov-01 law says suppose xn is a sequence of independent random variables. Xn is a sequence of independent random variables, then the tail events have probability either 0 or 1. Either 0 or 1. Okay, tail events have probability either 0 or 1. So what is, we won't go into the proof of this, but what is the implication of this? Okay, now tail events have probability either 0 or 1 means any tail random variable would be measurable with respect to this. Okay, so if a random variable is measurable with respect to such a class where probability of every event is either 0 or 1, what can we say about that random variable? So let us try to check. So suppose C is a sigma field such that probability of A is either 0 or 1 for every A in C. Okay, and suppose X is measurable with respect to C. So X inverse S belongs to C for every Borel set S. Right, that is our definition of measurability. And we just now said that probability of every set in C is 0, 1. So what does it mean? It means that probability of X inverse S would be either 0 or 1 for every Borel set S. Okay, what does it mean? It means that X belongs to S either almost surely or it doesn't belong to S at all. And this happens for every S. Okay, this happens for every S. Means there is only one possible value of X. That's why it can either be in S or it can be outside S. Okay, you don't have like, for example, if X had many possible values and if some of them are in S, then you get the partial things, right? For example, if x has possible values 1, 2, 3, and if you define s as say singleton 1, then s cannot have probability 0 or 1. S will have partial probabilities. Whereas now we are saying that for every s, probability of x being in S is either 0 or 1. This implies x has only one possible value. Correct? Therefore, x is a degenerate random variable. Okay? X is a degenerate random variable. So, any random variable which is measurable with respect to a sigma field consisting of events with probability 0 or 1 only is a degenerate random variable. Hence, Kolmogorov-01 law tells me that if I have a sequence of random variables for which say limit exists or lim_sup exists or lim_inf exists, then those lim_sup, lim_inf, etc. would be only degenerate random variables, because then only they can be measurable with respect to tail sigma field. Okay, so let me stop here. Thank you.